it should be done in command line, I think.
Yeah, it's a command line.
Command line will need Conda install.
What am I doing wrong here? It's embarrassing. I thought I had this already. I've run this last semester. Where is that? Package not found.
I think we have to write import SK image.
I've imported it.
I think you can also import from Jupyter Notebook inside here. So I've put the link on the chat, Ben, if you want to.
Okay. Where's my chat?
Because the command line might not be linked to the same.
Yes. Yeah. So I can pip install from Jupyter Notebook. It says okay. I never have done that. Let's put in a new cell here.
Install package name.
Yeah.
Exclamation mark. Yes.
Sorry.
Yes, pip install.
Pip install package name.
Yeah.
SK image.
Yeah. Yes.
You put exclamation mark. You put exclamation mark for the pip, I guess.
It's done.
Try again.
Yeah, the command worked. It's just
But it is asking to restart, right? It is asking
you don't need to restart. No
I
explanation.
think in the terminal you have to type pip install scikit image.
Yeah, that's what's going on. I'll do it here.
Yeah, scikit image.
Scikit image, that's what it's called.
I think you can try P3 also.
Yeah. Yeah, thank you. Scikit image, that's what I needed. Guys know what happened. I upgraded to Python 3.8 and I've probably broken everything. Never upgrade anything. That's the lesson. There we go. All right. Cut that. See if that's going to play nice. There we go. Right. Sorry about that, everyone. Thanks for the help. So there's Chelsea, our cat. This is what we're going to be doing the singular value decomposition on. So we've got here, we're going to import from the linear algebra library SVD, which is the function that we want. And we're going to take the original shape. So this is a NumPy. This is the CAD image we've set up is it's going to be an array, and so we can take its shape to get the original shape. We will want that because we're going to look at the we're going to be looking at the compression ratio later on in the task. So the task in the script says that you want to explaining the meaning of the lines in the first 5 cells. I think we're on top of that. And then down here, you see it's given us the example code for reconstructing the image from our SVD, and we've got these question marks in here, which are not good Python. And what we need.
Ben, do you mind zooming your screen?
Zooming in again. Yeah.
Yes, please. Yeah. Thank you.
My apologies. There we go. And so we've got these question marks here, which are what need to be filled in. So this is defining this compress function, and then this function. We're going to talk a bit more about functions later on in the workshop. This has these 2 arguments, which will feed it to run it, which are image and k. So image is going to be our image. I think we know that. And k is the singular values that we're using for the reconstruction. So here's the output of the SVD, and then in here we're going to want to put in some values to make this reconstruction work. So does anyone want to shout out what they think we should put in there?
Excuse me, can you mute yourself, please, and only unmute to ask questions?
Okay, so does anyone want to take a guess? Or even if you're feeling a bit rusty on your SVD or can't remember, you could use this by a process of elimination. There's only one variable that we have that we can really that isn't yet used in this function, right? And that's k. Now that may not be the most mathematical way of making a decision, but as you know, in terms of debugging Python code, that's a good place to start. If you've got a variable that's not being used, maybe that's what it should be doing. And actually, if we look at this, indeed, that is what we want. We want to be taking the dot products of these matrices along all columns, but also up until k. Okay, up until our top value of singular values. Okay, and that's where those would go. Okay, do check that against lecture notes on this in case. The proof will be in the pudding when we try and use this function and whether it does what we want it to do. There we go. We'll run that. So now that function exists, and then we want to apply that function. Going back to the script, it wants us to try a bunch of different k values up to 300 and have a look at what it does. So what we'll do is we'll set up a cell where we can set that value. Now you could do this with with for loop, which we'll be looking at a bit later in the class. But for now, we're just going to do this kind of the long way around. So this is how we will call our function, right? The cat image is the image we're going to be putting in, and the k value is the value that we're putting in, that we're setting just above this here. Okay. And now I just need to, there we go, add another bunch more cells. Sorry about that. There we go. And now we want to plot this. We want to plot in the script where we're asked to plot an x-axis, one plot with which is going to plot k against the compression ratio, and I think we also want to have a look at the reconstructed image and check that it's not done anything crazy, right? So we're going to make two plots, which means we want to use subplots, and we're going to use this pyplot to do this. So we set up subplots, one row, two columns, and this is going to be we're going to use these sizes for these figures, and these are the two objects that we're going to have there, the figure and the axes. And this is the compression ratio that we want to do. Now this is a bit. So what we have is our original shape that we got earlier, and so that's the pixel area, the original pixel area in the denominator, and then this is going to be the size of the reconstructed image. Okay. And then we just times it by 100 to make it a percentage, and then we're going to make we're then going to give our y-axis its properties. I'm just going to cut and paste all of this into here, and we're going to do an image show on the right hand panel. Okay, so then we can run this one, and here we go. For a k of 50, we've got this curve, and we've got a compression ratio of about 30%. We can put that up to 100, which I think was the next one. And we'll run this again. Starting to look a bit better. I think I'll skip out some steps. Go up to 200. And then the final value was 300, right? So, I mean, I don't know about you guys. I don't know if I'd...
So can you please zoom out?
Zoom out? Yeah, so we can compare them a bit. There we go. There's that cat at 300. This obviously has been plotted on a different scale. But I would say I don't think there's that much difference between the 100 and the 300, right? Yeah, I'd say that this
value has increased because at 300 it looks more defined.
You think? Yeah, it is sharper at 300. I think there's less lost.
They've cleared the noise, I think.
Yeah, although I think I think that you gain quite a lot in the lower values of K though, right? And then it doesn't improve quite so quickly, which I think is kind of what this curve is telling us. Now, I don't know what's happened to the titles on this figure. There's supposed to be a title, some axis titles on there, but I guess I didn't set them. Did I not set them? I didn't set them. Okay, so that's task 4 anyway. Are there any questions before we move on to the kind of the more generic Python tasks? This is the most data sciencey section of the practical, where we actually do some kind of something that you might find yourself doing as a data scientist.
Sir, can you explain the compression ratio formula again? I missed it, sorry.
So this the denominator here is the number of pixels in the original. So i.e. the number of values you need to describe the original image, right? And then up here is the number of values you need to describe the sorry, we've got some
and I will click mute all, and then please unmute yourself.
Sorry, I forgot to unmute myself. Right, and then the numerator here is telling you which how many values you need, if you like, the size of the matrix that you need to unpack, to reconstitute this compressed image. So it's the ratio of values between the total number of pixels on the original image, which is the number of pixels you have, and the encoded information that you have as a result of doing the singular value decomposition. Does that make sense?
Yes, thank you.
Okay.
Yeah, and I have one more question.
Mm-hmm.
With giving a K value as a 300, I don't find any difference between the original image and the compressed image. How? I mean, it's the same, like original image is also same, and we don't have any blur of the image over here.
So sorry, I my internet just broke down for a second there. Could you repeat the question?
Yeah. I don't find any difference between the original image and the K being a K value 300.
No, and actually, if you look at this compression ratio, at a K value of 300, I think we actually are using more values to reconstruct the image than there were originally. So I think the 300 is not a very efficient compression, right? And kind of pushing it down to 200 or to 150 is where you might start to actually have some compression. There we go. So now we're down below 100. But I don't think there's really perceptible difference between that and that. This is a larger image, right? And then I think if we go down to 50 is when we maybe see some. Maybe that's a bit more blurry. Does that make sense?
Only here we are just reducing the image size or image quality also.
So this compression will reduce the image quality as it reduces the image size. It's not like a lossless compression.
So it does not reduce the image quality.
I would say that has reduced the quality. I'd need to plot them both next to each other, but I think at 50 you can see a difference, that it is more blurred. So other people not convinced?
No, because we see the same quality. I mean, like even the original, it's look like an original size, but it just zoomed out.
I think the size might be changed. That's it. There is no change in the pixels, quality of pixel.
No, there will be most be blurry.
But because of the image that we have taken, we are not clearly depicted. Otherwise, like the image is blurred actually.
All right, I'm going to plot the. I'm going to plot the original next to it, and we can have a look. Let's have a look. There we go. And then this is called cat image, isn't it? And we'll take the axis off on it. Here we go. Let's see if that works. There we go. Right. So I'm convinced that the one on the right is less blurry than the one on the left, particularly if you look at the nose.
Yeah, nose and eyes. Yes.
Yeah. So this, it does reduce the image quality, but equally, it's a 30% reduction in the amount of data you need to store it. So maybe that's good value. Okay. But yeah, glad. I think we should use it. Always plot the original one next to the old one.
I have a question regarding a practical example of SVD and compression of images. Like, could you tell us that where in real life applications would be able to use this type of function to basically compress images and then basically plot results based on those compressed images?
So I'm not really super familiar with sort of commercial image compression code. So I couldn't tell you off the top of my head if there are any really popular
like, for example,
ones.
there are software, there are online websites where basically you compress your images and PDFs. Is it the similar? What we're doing, is it similar to that, or do we have other applications for this?
Okay, so I'll answer that question first. I couldn't answer that one as to what image compression algorithms those websites use, but there are obviously the range of image compression standards like JPEG and so on. And I don't know if they use singular value decomposition or some relative of it. But in terms of the kind of work that you might do where you might want to use it, if you have lots of image data.
I think I will unmute all and then unmute please.
Okay. I think if you have image data that you want to process as part of a project, as as part of your data that you're working with, you may want to employ a simple compression algorithm like this that you kind of can get under the hood of, or that you can implement yourself, because then you may use the outputs directly in your analysis of those images. If that makes sense.
Yeah, and does the compression affect our result, the analysis we perform in any way? Like if we use a lot of compressed images, would the result be different from the result we would get if we use the original images?
It would wholly depend on the kind of analysis you were trying to do on those images. There are certainly ways you can imagine it would affect it, because you're using a particular you're carrying out a particular set of operations, which will change the scale over which you have structure in the image, right? And so that may, if you're doing an analysis that looks for kind of scales of structures in images, then using
like facial recognition, for example.
Result. Facial recognition, I don't know. You need to find someone who was kind of familiar with the networks they use for facial recognition. But I think those tend to always have structures on kind of bigger scales, just from my limited knowledge, right? They look at distance apart of eyes and nose. And
PCA is also used for facial recognition.
PCA is a part of it, yeah. PCA is used in that.
Would it affect?
So I don't think that this kind of compression should affect that very much, no. But anything where you're looking for the scale size of structures and things, which is something that I see a lot more. I'm an astrophysicist by trade, so people in astronomy use these kind of things and to look at use AI and deep learning and stuff to look at structure scales on images and things, and any processing like this can really affect those kind of results. And that might be the kind of thing if you're using image analysis for mapping or for any kind of Earth observation tasks, you may run into trouble with it. But yeah, it really depends on the type of analysis you're doing.
Thank you.
I shared in the chat a paper describing how SVD is used in image processing for various applications. It's 2012. It's ancient. It's not really recent one, but you would find deep learning as well benefit a lot from the dimensionality reductions by SVD before doing pattern recognition.
Thank you.
Ben, I wanted to add something on this. So I've done a couple of projects on computer vision, and that is where all the image is what we make use of. And now with use of CNNs, max pooling and convoluting them, reducing the dimensionality automatically with all ready-made algorithms like VG16 or Inception or you say any of those old school algorithms, it already does that. But I don't know how SVD does SVD beat those kind of algorithms in terms of improving image quality or recognition. So after you compress the image, our aim is to make the image as clearer for the algorithm to learn on, so that the algorithm can learn on better images and then make predictions or classifications, etc.
Yes, SVD, as you see, is a low rank. So instead of doing everything, you choose the best eigenvalues and you collect these only to work on, to build your CNN using the best representative instead of the redundancy of the whole image. So it is like compressing your model rather than working on everything that some of them doesn't tell you anything.
Okay.
So it might be in, if you were talking source code, it might be built in on some of the CNN packages. So you don't need to run the exact same code we are using here. This is the direct SVD you are doing yourself. But when you are using TensorFlow or Keras, it might be already included in a higher level call. So you need to read the help of any function and understand how it processes your data. It might be already giving you the image after it's being compressed to the most important rank only.
Got it. Does, just the last question, does SVD, can we use SVD for RGB images as well, or it only works best on grayscale?
I'm not sure, but if you want to research that, we can definitely find out.
I'll add on that. We can use SVD on RGB images because there's a library in Python, OpenCV. It's called OpenCV, and they use PCA with RGB images as well, and they use SVD in that algorithm as well.
Yes, you can. Theoretically, you can, but is it better or not? You need to research the latest surveys on that.
Got it. Thanks, Mal.
Okay.
Yeah, we can use another library for image compression.
Yeah, this is a tool. You will find it already built in many other tools. So Ben have used sklearn today, Scientific-Kit Learn today, the SVD implementation of scikit-learn. You will find it implemented in so many other libraries using different algorithms. Remember in last week practical, this week practical, we showed when you do it by hand, you do the mathematical notation on Python only, the result will be different than the SVD implementation in the scientific kit because of the standardization, some of the implementation details. So similarly, if you use one done by TensorFlow, might be different slightly. So you need to read the algorithm exactly, how it's published and what it's assuming in the data, or how it's pre-processing the data. What are the parameters? You can send the parameters, say how much compression you want, different algorithms to apply. So read the parameters and read the help of use the question mark and the help.
Yeah. Okay. Thank you. So it's great to. It's great to actually have a lively discussion about this. Many practical classes, people stay very, very quiet. So I thank you all for getting involved and discussing these things, because that's why it's better than just watching a video. So that was, we've got 20 minutes left. So I'm going to move us along a little bit, although this is actually, this section was the kind of I would say the most kind of the bit of the practical that we need to spend the most time on, I think. So I will move on to the rest, though, for those students that are less familiar with Python, because the rest of the practical class is really looking at some kind of I don't want to say basic, but fundamental functionality in Python that will be very familiar to people who've programmed in other languages. But if you're not if you're new to programming, this is stuff that you need to learn and get comfortable with. So, and this is about the first part of this is about defining your own functions. So in Python, as in all pretty much all languages, you can define your own functions, and these functions are contained in a certain way. You have some syntax that tells that denotes when the function starts, what the input is, and then something else which shows when the function stops in the text file, and also what its output is. And in Python, this is done with the def command, and then your function, and the brackets contains your parameters, your inputs, and then after the colon, on the next line, indented. So white space is really important in Python. So one indentation in, you then have your code. So all the code that you have in your function will, at its start column on the page, if you like, will be one indentation, one tab indented in, and then at the end of it, the way you denote that the function is an end, you use the command return, and then you return the values that you're going to output. Okay, and that's this here. So this is this bit of the script is explaining this, and then we're going to work through some examples where we make a function that does some work that we need doing. So this example is a function which adds two matrices, 2 by 2 matrices together, A and B. And you can see this code, this code here highlighted. So this needs to be added to the notebook that you're working in. And then you can see that it does what you want it to do. I'm not going to do that now. I'm going to jump on to task 5, which is then defining another function. So please do work through this example and check that it does what you want it to. Task 5 is following on from that. We're going to define a function which adds values along the diagonal line of a 3 by 3 matrix. Now, we can do that with linear algebra command diag and take the sum of them. But we're going to make a function that does it more explicitly. So I'm just going to bring over a notebook to this desktop, which has these examples in it. And is this the line? There we go. Yes. So this is the function that we're going to do. It's called trace sum, and there's a nice comment here. Always comment your functions. Give them a name that means something, and comment them. And the input is going to be a matrix X. Okay. And what we're going to do is add these diagonal values in together. We're going to sum them. So hopefully that makes sense. And then that value S is what we return. Okay, so this is a really basic function. And then we're going to apply it here. Let me zoom in again. There we go. So we're going to make this array, which is what we're given in the notebook. Okay, here, with the rows 1, 2, 3. Second row 0, 10, minus 5. Bottom row minus 2, 11. And then we're going to get that trace sum. Obviously, I haven't imported NumPy. There we go. And we get 22. Now, they didn't give us the expected answer, but I'm going to tell us that's correct. So that's a basic example of creating a function. We're going to move on to some string operations and dictionaries, and then we're going to be looking at lists. I think a bit later on. So not a huge amount of time left. So strings can be just simply added if you assign them to a variable. In task 6, somewhere down here, we're going to be looking at these, doing some string operations, putting things into lists.
And yep. Can you zoom in your PDF file?
Sorry. Okay. Yeah. So we're just going to work through some examples of doing some string operations, which we just combine with plus signs, and then we're going to look at lists. Lists come up a lot in Python, and you can mix different data types in lists. So each entry, you can have float values mixed with integer values mixed with characters with string values. You can also put other types of objects into lists. So those come up a lot as ways of moving things around. Here we go. So this is the string operations, and here's setting up a list. And here we've mixed integers with strings, and then we're going to use the insert attribute on this list to insert different extra entries into the list at different entry points. So the way you use insert is fairly intuitive. The entry that you want to insert the thing into goes first, and then the thing you're inserting comes second. So in the task, it asks us to put an E into the list between the 1 and the 2, and then an M between the 2 and the 6. And I'm going to get myself confused now. The counting. We'll see how it works. So we do this and we go, so it goes after so the 3 goes between the second and the third, between entry 0, 1, 2. It becomes entry 3, right? So I always get confused by these things, so excuse me working out in my head again. And then we're going to put a 0 at the end, and that uses append. So you can append things. The most common thing, in fact, I very rarely insert items into lists, but quite often you append lists to lists, or items to lists. You can only append a single item using append, and there's another function for sticking 2 lists together. So that's lists. Then dictionary. These are denoted with curly brackets, and they're kind of like a special case of I think of them as a special case of a list where each entry has some matching. Sorry. No. So we create this dictionary. I'm going to guess that these are ages along with our names. Okay. For some reason we've got the same cell in here. Okay, and so when you look up a dictionary, you get the attribute of the item in there. So this is a classic way for storing parameters that you're passing into functions and things like that. So you can set their values and not just have to remember which number they are in your parameter list. But there's lots and lots of other uses for dictionaries. So dictionaries are a very useful feature in Python. Particularly, I say that as someone who does a lot more programming in Fortran, where I have to keep track of which argument number different things are when I'm passing things back and forth between functions. So that's dictionaries. Get to grips with them. These are kind of just, this bit of this practical is really kind of examples of things you'll need to learn how to use in Python. So do work through these examples. If statements work very similarly to in other languages that some of you may have met. Sorry, I've jumped forwards. Am I? Okay, so yeah, no, they so you do an if statement is indented with a tab indent, and you can join several if statements with elif, which is else if, right? And then if those things aren't met, you have an else. Okay, and that's typically put at the end of a set of ifs, else ifs. So there's an example here that we have a condition here where we ask some user input, and then depending on what you put in, it gives a response. So these you can join these logical statements with these with these pipes, and then we get some output. And if you don't give it 1 to 3, you don't get a valid number. So I give it 5, didn't add a valid number. 2, we get hello. So this is a nice example, obviously, of using input as well as the if statement. So this is given to you in the script, and the task 7 is to play around with it, right, and get used to how it works and change it to do these different things. Okay, I'm not going to go through that right now because I think this is something that really there's no point in me showing you how to change the values in this bit of code. Put this code into your notebook and do these bits of practice. Okay. Okay. So these, just for the last few minutes, we're going to look at a few different ways of iterating things. So this is tasks 8 and 9 in the script. The point of these is to show you different ways, as I say, to iterate through lists or arrays. In this case, what we've got is a list of student names, and we want to print them out one at a time. And the simplest way to do this is to use this method of iterating. And we say for some variable, in this case one name, in student names, which is in our list. So we take a variable, which is essentially a counter, right? And it works through this list, and we print it out at each cycle through there. Okay, so this is gonna, if you get this, what this is going to do is go through and print this out one at a time. So we're going to get one of these printed out on each line of the output. Okay, now you could do something more complicated, right? You could concatenate 2 of them and iterate through like that, or if these were numerical, if these were say that these had different values associated with them, you could do different operations with them in your loop here. Similarly with this is a string. It's not a list, but it works the same way. We've got a set of values, and we can just work through printing out one value in each point of the iteration, and this will instead print hello world vertically. Okay. This is quite a powerful way of iterating through lists and other sets of information. With numerical values, we can use inequalities or to work through. This is more intuitively a counter. So we've set some variable, right? And while that variable is greater than some other number, in this case, while num is greater than 0, we're going to do some operation. In this case, that's printing out that value and then subtracting 1 from it. Okay. Obviously, I'm sure you can imagine more complicated things we don't want to do with something like this. And so what this does, as we can see, is prints out num equals 4, 3, 2, 1. But again, this is this is a classic way of doing some iterative process. For example, you might have some kind of tolerance condition, right? That if your tolerance, if your error or variance on some model drops below a certain value, you're going to stop doing the iterative process that you're following. This is the kind of loop you might use for that. And this is another another kind. It's doing essentially the same thing, right? It's just in reverse. And the kind of for loop that the kind of loop, iterative loop that we haven't shown, I'm going to show, is the one that, despite all these really clever ways that Python lets you do things, because I write in Fortran, I'm going to add for I in range 0 to some number. This is the kind of the classic loop if you're wanting to just iterate through values. And if you can't easily cast your problem into one of these ways of doing it, this is probably not a bad catch-all to keep in your back pocket. And this basically does some operation for each value in this counter range. Okay, but I think of each of these iterative loops, while loops and for loops, as kind of more efficient ways of doing something that I'd probably do with a for loop like this or a do loop in some other older, more clunky language. And I think we're at the top of the hour now, so I'll just I raced through those tasks at the end, but I'm hoping that they're the kind of things that it's really better for you all to have a go at and play around with on your own. Does anyone have any questions about this stuff?
Yeah, so my question will be, are you able to share this Jupyter notebook where you have your scripts on with us?
Yes, the solutions, the solution notebook will be shared on Canvas in a week's time, I think is what Yisun has said. There was a bit of a discussion about this on Canvas that you can see. But yes, we're not going to be posting the recordings to these workshops, but after time to do these, to have a go at these problems, the solutions will be posted. But please do, as I said last time, please do have a go at doing them yourselves. Even just these bits where it's just saying, type this stuff into a notebook, just doing it yourself, it starts to create, I don't want to say the muscle memory, but it's like as I said before, any language, right? You learn it by using it. And so in the first instance, just copying out examples and then, messing around with them is a good way to get used to writing the language, particularly, just in terms of the white space, that's a classic thing with Python, is for people to lose track of their white space. Editors like Jupyter Notebooks are really good at ensuring that your tabs are correct by default, but obviously it's by writing functions and changing them and playing with them, you'll get used to making sure it's right yourself as well, because errors in writing things down is in white space and the wrong kind of brackets, square brackets instead of curly brackets, all this stuff are the kind of things that cause errors. So yeah, do please, the solutions are coming out. There's no point in you just hitting play, hitting run through a Jupyter Notebook of solutions. You're not going to learn anything that way. You need to be working through these examples and typing them out yourself. Okay. Okay, so I'm going to stop sharing. Because we're at the top of the hour. It's the end of the class. Please, thanks for all coming. Thanks for those of you who got involved in the discussion. That's great. Really appreciate the discussion. And everyone, please do attempt the problems as much as you can before these workshops, because I think you'll really get a lot more out of it if you've had a go at these things. So yeah, and thanks to Niall for helping out and answering questions much better than I could on SVD.
Thank you, Ben.